Welcome back. This is the second and last section for chapter 13. So we will continue studying solids and modern materials. We're going to concentrate now on the modern materials. So what are we doing here? We're doing semiconductors. We're going to study the band theory, which is based on the molecular orbital theory that you study on Chem 1411. Once we go into the band theory, we're going to talk about a valence band, conduction band, what is the band gap, what is an N-type and P-type holes, what is an insulator, and what is a semiconductor. We're going to try to relate how big the band gap is, which makes it insulator or semiconductor or conductor, and we're going to see that based on the periodic table trends like size and radius and so on. And we're going to see how we can control a semiconductor by determining if we're using an N-type or P-type hole. So before we move any further, we rarely get to cover the way it should be covered molecular orbital theory in 1411. So those of you that were able to cover it, this is a review. If you have never heard about molecular orbital theory, here is a quick review. Basically, molecular orbital theory tells us that when elements come together and make a molecule, you do not have like orbitals from one atom and orbitals from another atom overlapping together. What you have is an orbital that covers the whole molecule and is formed from those atoms that came together. So instead of having atomic orbitals, what you have is a creation of a molecular orbital. So let me explain myself. And I'm assuming you did electron configuration, orbital diagrams, and so on, and you know what a S and a P orbital is. I know at least you were able to get to that. So let's say that I'm trying to represent the molecule of hydrogen, H2, with a molecular orbital diagram. So I'm going to have one hydrogen combining with another hydrogen to produce a molecule of hydrogen. So one hydrogen, you know it contains only one valence electron. So we're going to represent that like that. And the other hydrogen only contains one valence electrons. So this only deals with valence electrons. And this is what's going to happen. Since electrons are so small, we know from chapter 7 on 1411 that the smaller something gets, the more it begins to behave like a wave instead of like a particle. So even though the electron contains mass and is a particle, is so small, like 10,000 times smaller than a proton, that it behaves more like a wave. So if I have a wave from one electron, and this wave combined with the wave from the other electron, and they happen to be on phase, so it's all aligned, then you get an amplified wave. So that's a good thing. That's what creates a bond. Those two waves comes together and you get an amplified wave. So that's very stable. So that's one of the possibilities, right? That the two waves are going to be aligned. That's a possibility. What happens if the second wave is not aligned? So one is up, the other one is down. When that happens, they cancel each other, which basically means these two electrons are not bonding together. So having two atoms with one valence electron each, you have two possibilities. Those two electrons can be on phase, which creates a bond and is stable, or those two electrons can be out of phase, canceling each other and not creating a bond. The way we're going to represent that on this diagram is we're going to do a energy diagram. Let me do that again. So we're going to do a energy diagram where the energy is increasing as we go up, and we're going to represent the two waves on phase by saying it's very stable, so the energy is going to be low. So we have our atomic orbital, which is a 1s1, and we have our another atomic orbital, which is also a 1s1. And I know you remember that from Chem 1. So the two electrons on phase, they come together and they become more stable than the atomic orbital, so the energy is lower than the atomic orbital. So the energy of the new bond is there. And because this is an s orbital and an s orbital, they're going to be overlapping head to head, and we're going to call that a sigma molecular orbital. And I know you remember that from Chem 1. How do we represent when the two waves are not in phase? Well, they are not making a bond, so they are not stable. So that area is going to be higher in energy. So on the left side, we have one atom. On the right side, we have the other atom. On the middle, we have the molecule. And the molecule is forming because those two electrons are coming together. So this is a molecular orbital. The maximum number of electrons you can put on any orbital is 2. And since you have 2 electrons, this one and this one, then those 2 electrons will go together on the molecular orbital. And then we said this combined with this to produce a bond, a sigma bond. And the other possibility was that they didn't bond, and we're going to say that's a sigma anti-bond. So that's the most simple molecular orbital diagram that you can have. This has to be, most of the time, has to be made by computers. They become so complicated. So I just want you to understand the concept, explaining to you the most basic molecule, hydrogen gas. And you can see the sigma bond, the anti-sigma bond. And this right here, this distance from here to here is the distance between the orbital that is occupied in comparison with the orbital that is unoccupied, or the bonding and the anti-bonding. So we're gonna call this a gap in energy. So we're gonna go deeper into that once we go into the band theory. So this is the molecular orbital theory. We're using atomic orbitals explaining the formation of a molecule. So quick review. So if you need more information on this, make sure you check the tutorial videos that I have posted on Canvas. You can also go back to chapter 11 on your textbook from last semester. And this is just the same concept that I just told you about wave canceling or not canceling. And you can use this. You probably have used this before. If you have headphones that are noise canceling, that's what happens. Let's say that we have a plane over here. You're on the tarmac on the airport making a lot of noise. Your headphones capture the noise. They send it through the computer setup. It goes into the computer setup where it's duplicated on the opposite phase. When they come together, they cancel each other. So the concept of the wave can be used on a lot of places. We are using it with an electron. So this is basically what I showed you before. Two hydrogens, they can come together giving you a molecule, or they can not bond. Anti-bonding and bonding. The formation of the bond is in phase. The anti-bonding, where you have a node in there where they do not bond, that's because of a two out of phase wave. So that's the molecular orbital theory. So how do we use this on the band theory? What is band theory? Well, let's do it with metals, because we're going to be using this a lot. Remember, I told you before that we explained some of the properties of matter by using the sea of electron model that we discussed before, or by using the molecular orbital theory, which we just reviewed. So with a metal, let's say that we have a metal by itself, lithium. With lithium is on group 1, so lithium have 1 valence electrons. So that's what you see there. However, if you combine on a metallic solid, if you combine two lithiums, now you have 2 electrons. And you have the bonding and you have the anti-bonding. What about when you have 3 lithium atoms? Now you have 3 electrons. So these are my bondings, and there's nothing on the anti-bonding. And notice this. This is the distance between the bonding and the anti-bonding. Now this is the distance. Now this is the distance. So if you were going to happen to have a piece of lithium in your hands, you're not going to have 1, 2, 3, 4, or 5 lithium atoms. You're going to have trillions and trillions and trillions. Remember Avogadro's number, 10 to the 23rd? You're going to have so many atoms together that this band, this gap between the bonding and the anti-bonding, the more you have, the smaller it gets, up to a point where the gap is basically gone, depending on the elements, and the bonding orbitals, they start overlapping over each other. So they become, instead of discrete orbitals, now you have like a band. So that's what we call this, the band theory, because those orbitals, molecular orbitals, are overlapping one over the other. They're getting closer together, so you cannot distinguish one from the other now, like one and 2. Now all you have is a band. So the more atoms you have, like in a solid, the more this band theory makes sense. So for example, if we have a unit cell, like the ones we discussed earlier, where you have a lot of atoms, the atomic orbital of each one of them is going to give you a band where you have electrons, and another band where you have no electrons. And there's a empty space in between. So once more, you're going to have electrons in here. So in here, on that, you're going to have electrons in there. And those electrons have energy. So if that energy is big enough to jump there, then you have electrons moving, which means electrons moving means that you have a current. So you are there's a current of electrons, or you're creating an electric movement. But so whenever the electron moves in there, they are conducting electricity. So we call this the conduction band. We call this one the valence band because that's where you put all the valence electrons. So if the electrons from the valence band have enough energy to jump into the conduction band, there you are a conductor. You are conducting electricity. But what happens if your conduction band is like this and your valence band is like that, and your electrons can only go there? On that case, the electrons do not have enough energy to make it to the conduction band, so there's no electricity being created, there's no conduction. So we call this an insulator. An insulator will be a solid where the difference between the valence band and the conduction band is so huge that the electrons cannot move from one to the other. Diamond is an excellent insulator. Plastic is an insulator, and so on. Usually, you're going to have an insulator where when the energy difference between one and the other is bigger than 5 electrovolts. Anything around 5 electrovolts or bigger is going to be an insulator. What happens when you have your valence band and you have your conduction band and there's not even a gap between them? When that happens, you have a conductor. Electrons are going to freely move from one to the other, creating conduction, creating electricity. So a conductor will be when there's no band at all, or the band is so small that the electrons can move really easy from one to the other. So what happens when you actually have a band and the band happens to be less than 5 electrovolts? Remember, 5 electrovolt is the forbidden number. Once you get to that point, there's no way the electrons will move. There's no conduction at all. So what happens when your valence band and your conduction band have a band gap of less than 5 electrovolts? On that case, then you can control it. You can change the material to make the band smaller. Because the band is not that big, you can apply energy, could be heat, could be electricity, to force the electron to jump. If you try to do with something with 5 electrovolts, that's not going to happen. That's the forbidden one. So this is where you're going to find your semiconductors. Your semiconductors are going to be when the band gap is less than 5 electrovolts, but not too small, so you can control. That's where our technology is today. We design materials where we can control the jump of electrons, therefore having something that conducts electricity or doesn't conduct electricity, one and zeros, and all that kind of stuff. Diodes, LED, everything you can imagine that you love about our 21st century, that's most likely related to semiconductors. So important elements to understand: the band gap, the forbidden one, what creates a conductor, a semiconductor, and an insulator. And here's the example. This is what we're talking about. A small energy gap, semiconductor. Large energy gap, insulator. What is the forbidden energy? 5 electrovolts. Anything around 5 electrovolts is going to be an insulator. And your conductors, like for example, iron. A solid piece of iron will conduct electricity. So never put a piece of iron inside an outlet because you're gonna be up for a surprise. So at this point, pending more review on your part, you know what the valence band is. You know what the conduction band is. Valence band is where the valence electrons are located. Conduction band is where all the anti-bonding, which is empty, are going to be, those orbitals based on probability. So it's empty, so the electrons can move there. Band gap is the difference between those two bands in terms of energy. And then we're going to talk very soon about N-type and P-type semiconductors. So how can we relate the difference between the valence band and the conduction band to periodic trends? Well, let's do some problems. Or some more information. So if we have a solid made out of carbon, the particular example diamond is going to have a band gap of 5.5 electrovolts above the forbidden number, so therefore an insulator. A solid, and these are covalent networks. So silicon is going to be a lot lower than carbon with 1.11. So that's a semiconductor. Germanium, a network of germaniums is going to be 0.7, semiconductor also. Tin, the band gap is really small. So that's a conductor, and a conductor is a metal. And lead, there's no band at all. So that's definitely a metal, which are conductors by definition, because metals conduct electricity, right? Would you expect copper to be an insulator, semiconductor, or conductor? And your answer had to be, it's a conductor. That's the wire we use for electricity, copper. So why these numbers? Where are these numbers coming from? Why are carbon bigger than silicon? And the answer will be as follows. When we look into the periodic table and we look at group 4, you're going to have carbon, silicon, germanium, tin, and those are the ones we're going to focus on. So if you remember, this is going to be on period 2. So you're going to have your nucleus, and then you're going to have one energy level, two energy levels. Silicon is going to be on period 3. You're going to have the nucleus and one energy level, two energy levels, three energy levels. Tin is going to be nucleus, one energy level, two energy levels, three energy levels, four energy levels. Can you see that the size is definitely increasing as you go down? So what happens? If I try to put a carbon connecting with another carbon, the bond is going to be like this. From nucleus to nucleus, that's how we measure the length of the bond. What if I put tin with another tin? Then the length of the bond is going to be like this. Really easy question. Which one have a longer bond? This one will have a longer bond. So if this one have a longer bond, would you expect a longer bond where the electrons are farther away from the nucleus to be the strongest or the weakest bond? So the closer those two nucleus are, the electrons that they're sharing are going to be closer to the nucleus. So this will be the stronger bond. This will be the weaker bond. So would you expect the stronger bond to be the most stable or the least stable? The stronger the bond, the lower the energy, which is what nature always wants. So therefore, the most stable. So if I have an energy diagram, and I'm doing carbon, which is the most stable, then it would be low here, while tin is going to be higher, the weaker bond, higher energy, because it's the least stable. So as the bonding goes down more stable, the antibonding will go higher. On germanium, as the bonding goes up in energy, the antibonding will go down. Therefore, we can visualize that the band gap on the stronger bond is going to be bigger than the band gap between the weaker bond, which is what we see. We see a bigger band on the smaller atom compared to a super small band for the bigger atom. So that's how you can rationalize the size of the band gap in terms of the periodic trends, in this case, the radius. So let's do a problem. Will gallium phosphide have a larger or smaller band gap than gallium nitride? Well, obviously, gallium is the constant, right? So we're comparing nitrogen and phosphorus. So that's how they're located on the periodic table. So this is the biggest one, which is going to give me the longer bond measured from nucleus to nucleus, which makes it the weaker bond. And the weaker bond will be less stable, which tells me that the nitrogen, which is smaller, is going to be a smaller bond, stronger bond, therefore more stable. And the gallium phosphide is going to have a longer bond, which is weaker, which is less stable, higher energy. And the higher the bonding goes, the lower the antibonding goes, which gives me a bigger band gap on the gallium nitride compared to a smaller band gap on the gallium phosphide. Let's do another one. Zinc selenide and zinc sulfide. What's the common element? Zinc and zinc. So what we're doing is comparing selenium and sulfide according to the periodic table. Oxygen, sulfur, selenium. So the selenium is the bigger one, which makes the longer bond, which makes the weaker bond, which means higher energy. The weaker something is, the least stable is, which means higher energy. The higher the energy, the bonded, the lower. So this one goes higher in energy, this one goes up in energy, which means it's going to have the smaller band gap. So this one will be the one with the smaller band gap because the element accompanying zinc is selenium. Selenium is bigger than sulfide, which gives you a longer bond, which is a weaker bond, which means it's higher in energy position, which means the band gap are closer together. So selenium will have the smaller, zinc selenide, we have the smaller band gap. Your turn. So that's what we just did. We related the band gap to a periodic trend. What periodic trend? The radius or the size. By relating it to the resulting bond, length, strength, and energy. So what about N-type or P-type? Remember that everybody wanted to be like the noble gases back on 1411, General Chemistry 1, and the noble gases have 8 valence electrons. So that number is kind of important in nature. So this is what I'm going to call the magic number when we talk about semiconductors. So N-type will be when you exceed that magic number. Our P-type will be when you have less than the magic number. So when we call something dope or undope, it's going to be when we start putting, when we don't fill up the valence shell or the valence band, or when we put from the beginning electrons on the conduction band. So a N-type semiconductor is one that has more electrons of what you can put on the valence band, so you're going to have to put them on some of them on the conduction band. P-type is going to be one where you don't have enough electrons to fill up the valence band, and you still have nothing in there. So that means that there's space in here to move electrons back and forward. So this is already creating electricity. So how do we know if you have an N-type or a P-type? Well, what we're gonna do, we're gonna look at the an alloy that we're gonna have. So if I have a network, a solid that contains those elements, each one of them, and I put silicon into it, am I creating a P-type or an N-type semiconductor? Well, this is how we do it. Gallium. Gallium is right there. And this is group 4. Therefore, we have 4 valence electrons coming from gallium, and we're combining it with silicon. Silicon is right there with also 4 electrons. When I combine those 2 sets of valence electrons, I get 8. So this is not N-type or a P-type. That's just the magic number. So you haven't done anything to that one. What about arsenic? Arsenic, you're going to find it here, which is group 5. Therefore, arsenic is going to have 5 valence electrons. Silicon have 4 valence electrons, which give you 9 electrons. 9 is bigger than the magic number, so you have more electrons. So that's a negative dope semiconductor. And now you are adding silicon to a network of arsenic, forcing it to be a N-type semiconductor, which those electrons are going to start moving now. What about carbon? Carbon have 4 valence electrons. Silicon have 4 valence electrons. Therefore, you haven't done anything. So this is undoped. You haven't doped anything there. This is undoped also. And this one is negative dope. What would be an example of a positive dope? Well, you can probably take aluminum and add it to gallium. So if I have gallium dope with aluminum, gallium will have 4 valence electrons. Aluminum have 3 valence electrons. So now you have 7. and 7 is less than 8. So that means you still have a space on that band gap because you haven't made it to 8 yet. This will be a p-type semiconductor or a p-dope semiconductor. So that's how you do that, by focusing on how many valence electron each element is bringing into the game. So your turn. And with that, well, let me show it to you a little bit longer, sorry. So with that said, you should have a pretty good idea of what a valence band is now. Same with the conduction band. The band gap, remember the forgiven number. You now know what n-type and p-type are. P-type is missing electrons, so we call those holes. Depending on the band gap, if the band gap is more than 5 electrovolts, you're going to have an insulator. If it's bigger than 0.08 but less than 5 electrovolts, you have a semiconductor, which you can then, as an engineer, you can control. We know how we can relate the elements on the periodic table to the size, the relative size on the band gap. And now you know, given an element, you can start selecting from the periodic table what other elements will make it a p-type or n-type dope semiconductor. And with that said, we are done with this chapter. So make sure you review each one of those terms. And if is there anything that is not too clear for you, go back to the textbook. Make sure you look at the tutorial videos posted in there. Go to the Science Learning Center, come to my office, meet me on Microsoft Teams, whatever you need to do. I'm here to help you get this. So, or bring questions to the workshop. If you have any question that you want to ask during workshop, try to email it to me first. That way I can bring all the material that you need. So until the next one, we're done for today. So we'll see you later. Next chapter coming up, chapter 14. Take care.